Hello, my friends. Welcome back. So, we've been talking about timing optimization and different techniques that we can use to optimize a design with respect to timing. The first technique that we talked about was adding a layer of registers, and we saw that in the previous example and in the previous video. And in today's video, we want to talk about the second technique that we talked about, which is the use of parallel structures, right? And before we start doing the example for today, I just wanted to mention that depending on the design that you have, you can use different techniques. So not all techniques are applicable to, I don't know, like all designs. So that's why I'm not using the same example because sometimes it just doesn't make sense or it's not obvious. So I try to find good examples so that you can actually see like the proper technique for that example. Anyway, in today's example, I want to use the same third power circuit that we designed in the very first video, and we want to keep going with that. Anyway, let's get started. So this was our first design, right? The power 3, we called it. And then we saw how we can optimize that for throughput and how we can optimize it for latency. So we want to do something similar to this guy. Okay, so I'm just going to copy this to save some time. And I'm just going to go down here, paste it, and obviously uncomment it. And I'm just going to call that timing optimization. And then I want to go parallel structures, right? And okay, let's see what we can do. For now, let's get rid of the parameters. Again, I'm not really here to design like the whole thing and like write a test bench or something. I just want to give you the idea of how things work. And I'm just going to go 8 down to 0, which is like an 8-bit signal. And then here, obviously, it's a power 3. So 8-bit, it goes out to 24. But for the sake of simplicity, we're going to do 8-bit output as well. Again, this is not the most accurate design. I just wanted to show you the technique, right? So these are input-output ports, right? And now let's get started. We can get rid of this and start coding, okay? So let's go logic. Well, before we actually do this, I want to show you how this thing is done. So if I go here, I want to use the parallel structure. I think when I was talking about this technique, I told you how it works. So the whole idea is that you can use this technique whenever a function that currently evaluates through this serial string of logic can be broken up and evaluated in parallel, right? So the example that I told you was that, let's say you want to do like x squared, for example, that's x times x, right? So you can do this. And then to optimize it, you can say my x actually, let's say we're talking like an 8-bit value. So it has 2 nibbles, right? So A and B. And or you can just call that nibble A, nibble B, whatever you want to call that, right? So A is the most significant 4 bits of x, and B is the lowest significance 4 bits of x, right? So with this definition in mind, we can go x times x equals A times A plus 2A times B plus B times B. So this is the technique that we want to do. So we are breaking out because like this is an 8-bit multiplication and it takes time, right? So I'm dividing that into 2, or like in this case 3, and if like these were different, that would be 4 max. 4 by 4 multiplication. So 4 by 4 multiplications are much faster than 8 by 8 multiplications. So this is going to be a faster design in general, right? So this is the whole idea. And then once I have this, then I can shift this 8 time and then shift this 4 time and then add it with this, right? This is how it works. So this is what we want to do now. Let's get started. So I want to define a logic. I'm going to go down n-1 down to 0. And I want to call that xp1. Actually, let's define our signals as we go, because I'm not too sure how many signals we need. So let's remove this. And then we have a clock, so we can go always flip-flop, and then inside we can go at something like pause edge of the clock, begin, and this is what we want to do here. So what we want to do, we want to go the pipeline stages, right? So we want to go pipeline stage 1, right? And then what I want to do is that I want to have an x1, which is my x, and with my input data, obviously. So I need to define x1, and then I need xp1. Again, we've had this example before in the previous video. So if you forgot about that and like the pipeline stages and everything, make sure that you go back to that video to check that out. And then this guy would be also iData. Oops. iData. So here I need to go logic, and since everything we're dealing with is 8-bit here, again, not the most accurate, but you know what I mean. So expand to 8 minus 1 down to 0, x1, right? And we can just go here and go xp1 as well. So this was the first stage of pipeline, right? And then we can go pipeline stage 2. And what we want to do here is to basically go x2 equals x1. And these are not equal signs. These are assignments. So x2 gets the value of x1. And then to calculate xp2, which is the second power of x, we want to do the calculation that I showed you here, right? So now we want to go, let's just make a comment. I'm just going to go creating the partial products, right? So what I want to do here is to go xp2, and we need, because it's like the third power of x, a times b is like the same. So we have like 2 times a times b, right? This is like the term. So we have like 3 of these products, a times a times b, and b times b, right? This is the highest order because like this is the most significant 4-bit. So I'm just going to call that xp, the third term, which is like the most significant term. And then respectively, we can go down for AB would be xp2, 2, and this would be xp2, 1, right? So it will be obvious in a second. So I'm just gonna do this. My OCD kicks in sometimes. So what we want to do here is that we want to go xp1, right? And then obviously a times x1 a. And then I want to copy that and then do that 3 times. So the second one would be AB, right? And then the first one, which is the lowest significant one, is DB. So we need to define these guys, right? So this, well, we're going to define that in a second, but obviously like this is the most significant 4 bits of A. This is the lowest significant. This is also like the most significant part of X again, and then, yeah, so on and so forth. So and this would be the end of the second stage of pipeline, but we need to define everything that we're using here, right? So we can just go copy this and then do of that. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9 of these, right? So we can just like do this and be like, hey, do like all of them here. You know what I mean, right? So for example, here you go XP, sure, this guy, this would be XP 1B, and then so on and so forth. We define XP2 theory. So you define all of these, right? I don't really want to spend the time in here to like waste your time with defining all these signals, but we obviously define them all here. And then we need to assign this, like what is XP1A, well, what is XP1B, and you know, all of those things. So actually we should do this here because it matters. So X1A, we have that. X1B, we have that. And then XP1, oh, yeah. So now X1A, and then X1B. So we have X1A, X1B, XP1A, XP1B. So we have these. And then we can go, well, Jack. Oh, we could just copy those. That would be XP2, 3. And then let's copy this. And then do this. 3, 2, and 1. So X1A, right? This guy, when I'm defining this, I can go, this is X1A, that would be X1 7 down to 4, right? The most significant 4 bits. Or here, if you don't want the cell line, you just go 8 minus 1. X1B, on the other hand, right? That's the lowest significant, like the least significant 4 bits. So that'd be, you can go 4 minus 1 down to 0. Okay. And then we obviously need to do that for X2 as well. In that we were going to need this in the third stage, right? So I'm just going to add them here. X2A, X2B, that's this guy, oops, that guy, and then this guy, and then XP1A, XP1A, that's obviously instead of X1, that would be the most significant 4 bits of XP1, and then that goes here, like that. And then XP2, yeah, so that should do it for now. Yes, so we have defined XA1. We know what that is because we calculated X1 here. We know what X1 is. So the 4-bit goes in there. So you can define these as like 4-bit values, obviously. So you don't have to like use 8-bit values. You can use 4. It's like actually makes more sense. But anyway, you know where I'm getting at. And so yeah, we have X1A, we have X1B. We know what those are. And then we have XP1A because we calculated XP here, and then we're assigning them here. Cool. So that works. And then we go down here, and then we go pipeline stage 3. And in the third stage, right, we also need to create the partial product as well. So I'm just going to go creating partial products, right? And then here you basically want to do the same thing. So I'm just gonna copy these guys, bring it down with them here. Now it will be XP3 because this is the third stage of our pipeline. And these guys will be speed 2, 2, 2, and then obviously X2, not X1 anymore, right? And have we defined these? Yes. So we've defined X2A, we've defined X2B, XP2A. We haven't defined these, so we can just like bring these guys over and be XP2A, XP2B, we'd be XP2 and XP2 here. So we've defined everything. These guys, XP3. So we can just like copy these as well. Okay, I didn't really want to define them, and I thought if I won't, it's gonna be a bit confusing. So hopefully this part makes sense to you. All I'm doing is that like tweak the same code that we had before with 3 stages of pipeline. And instead of saying, okay, multiply those, I'm just like saying, okay, break down that 8-bit multiply into 4-bit multiplies, right? And that's all I'm doing. So now I have all the partial products, and all I need to do is to put them back together. So the first thing I need to do is to go here and say sum XP2, because we haven't really defined XP2 yet. XP2 would be XP2 part 3, right? And as I said before, we're going to shift that to the left 8 times because XP2, the third part, like if you look at this guy, right? 8 times A, you have to shift it because like there is, in this example, 8-bit example, right? So A is 4-bit, B is 4-bit. So when we are multiplying A's, if you want to like bring it to the same order, to the correct order, you have to add 8 zeros, right? It's weighted sum, right? That's what we're doing here. So we shifted 8 times here, plus we have A times B and B times A. So 2 times XP 2, which is A times B. And then this, we're going to shift to the left by 4 bits. And then once we have that, it's the final one, which is XP2, the first argument. So now we've calculated XP2, right? And we know, we've made that, like how we made XP1 here, and now we define XP2. And then once we have that, we just need to assign the output. So I can go data now. If I go here, equals, I'm just gonna copy this, not the whole thing, but just this part, and this will be XP3, 3, and 3, right? That's all you need to do. So if you look at the code and compare it with the one that we had, you will notice that the only difference is that I'm just breaking down 8-bit multipliers into 4-bit multipliers. And that makes your design to meet the timing, because 8-bit multiplication obviously takes more time than the 4-bit multiplication. And I'm doing these in parallel. So at each clock, I'm doing like 3 calculation, for example, here, right? 3 multiplication, but like 3 smaller multiplications. So that improves the timing. And yeah, that's about it. This is how you can use this technique, which I call the parallel structures. If you can, sometimes you cannot, and like data is dependently, there is nothing you can do about it. But in some cases, and in most cases, honestly, if your design didn't meet the timing, this is a good technique to use. You just break it down into like smaller pieces, right, and do them in parallel. I'm thinking about if there was anything else that I would like to add here, but honestly, I cannot think of anything. And that's all for today's video. If you liked it, if you found it useful, please give us a like. And if you haven't already, don't forget to subscribe to the channel so that you won't miss the next videos. And as always, thank you for watching me, and see you all in the next video. Thank you. You guys have a good one. Bye-bye.